Hey everyone, in this video we're going to finish talking about exponential functions. And so in the previous videos we've done these other objectives, so now we're going to be solving exponential equations. Okay, so in order to solve an exponential equation we just need this important property, which if you don't overthink it, it's very straightforward and hopefully it'll make sense when we work through these examples. What this says is if I have the same base raised to some power and I equal it to the same base raised to essentially the same power, then the powers are equal, or the exponents are equal. This is what it says. Okay, so like 2 to the x equals 2 to the y, then x must be the same thing as y. And that's because if I put some numbers here, and then if I say, well, what is this other number? Because there's an equal sign in between, then the only possibility is that 3 is what I was questioning, the question mark. Okay, so that's all that we're going to do with this property. We're going to set these bases, well, we're going to have an equation to start with. So the bases are going to equal each other. And then what you're going to do after that is you're going to say, well, if the bases match, if they're both the same number in the base, then the exponents must be equal. So we'll go ahead and set them equal to each other. The interesting part of these problems is that a lot of times the bases don't look like they match. And so all you have to do is an extra step at the beginning to make them look like they match. Alright, so we're going to solve each of these exponential equations. And notice in both of them, the bases do not look like the same number. This one has a base of 2, while the other side of the equal sign has a base of 8. And then over here in part B, this is a 9 as a base and 27 as a base. But that's okay, and I'll show you why. And so because on part A, 8 is a power of 2, we can write the same base. Okay, so we can make the bases match. So that's what I like to say. I like to say make the bases match as the first step. Okay, and so 8 is rewritten as 2 to the third because 2 is the base on the left, so we want 2 to be the base on the right. We want them to be the same, and that's because 8 is a power of 2. Okay, and now that that's the case, now we just use our property. Okay, so the property says that if the bases are equal, the same numbers, then so are the exponents. So essentially what we had here is 2 to the, I'll just pick another letter, A equals 2 to the B, and so that must mean that A equals B, and so that's what we have here. This is just setting the exponents equal to each other. Another way to kind of remember this is think of it as dropping the base. So drop the base from both sides. That's how I kind of remember that that's my next step, and I just focus on the exponents. So the exponent of x plus 2 must equal the exponent on the right side, which was 3, and then solve. So x equals 1. And that's all there is to it. The solution set is 1. And you can always check. So if you want to, you can check and just plug in 1 back into the original. So on the left side, does this equal the right side when I plug in our answer? So that's 2 to the third, which is 8. So yes. Alright, how about this next one? The left side has 9 as the base, the right side has 27. And so 27 is not a power of 9, but both of those numbers are powers of 3. So the common base, the number that they both share, is 3. Okay, you want to be thinking about exponents, that 9 is not going to be a power. You can't put any exponent on 9 to get 27. So you have to actually break down the 9 as well as the 27. You want to say what goes into both 9 and 27 if I'm thinking about exponents and bases, and that's why it's 3. So then we rewrite 9. We just take exactly where there was a 9 and we put parentheses around it, and we say that that's the same thing as 3 squared. And on the right side, exactly where there was a 27, we say, oh, that's the same thing as 3 cubed. And then we keep the exponents the same as they were before. So let me clear this up just a little bit, just so you see what we did. So we just took the two bases that we started with and rewrote them so that they had the same base. So make the bases match. That's our step 1 again. Make the bases match. Now that they match, you do want to do a little bit of simplifying, and then we can go ahead and drop the bases. Okay, so this step here, this is a simplify step. So if we simplify right here, we have a rule for exponents that we're going to use twice, once on the left and once on the right. The rule says over here, if I have the base raised to a power and then I raise that to another power, I just multiply those exponents. So we just multiply 2 times 2x plus 5, and on the right one we just multiply 3 times x. Then we use our property right here, we drop the bases and we focus on this exponent and we set it equal to this exponent. So that's our dropping the base step. And then we solve. So just solve this equation for x. And so if you just start simplifying and solve, you get x equals 10. And again, you can check. So let's do a quick check on this one. We have 9 to the 2 times 10 minus 5 power. And we are questioning, did we do this right? Is that the same as 27 to the 10th power? And so that's going to be 9 to the 20 minus 5 on the left. So that's going to be 15. And on the right, that's still 27 to the 10th. And if we go ahead and rewrite the bases now or use a calculator, we can verify that these are the same. I'm going to rewrite the base just to show you that these are the same. So on the left, 9, I'm rewriting that. So that becomes 3 to the 30th power. On the right side, if I rewrite that base, 27 is 3 to the 3rd. And so that becomes 3 to the 30th power as well. Or you can use a calculator just to show that that was correct. Alright, so you make the bases match, search for the common base. If you have, like on the last one, 2 was on one side of our equal sign, and so we just had to rewrite 8. But this one, we had to actually rewrite both bases. So that is your first step. Make the bases match and look for a common base. Okay, let's take a look at this one. Now we have the same base on both sides, however there is an issue with the fact that the right side has the base more than once. So the common base is good to go, it's the number e, but the right side is a little too complicated because in order to use the property that we learned, e to the a equals e to the b, then that would mean a equals b, the exponents are equal. We have to have the base just a single time on both sides. So this part here has to get simplified in order to use our property. Okay, so let's use our rules of exponents. So e to the x to the 5th, those get multiplied. So that's e to the 5x. And then over here, 1 over e to the 6th can be rewritten as e to the negative 6. And that's because if you want to go backwards, if you have a negative exponent, that says to move your base down to the denominator and take off the minus sign. So we're just going the other direction to bring it back out of the denominator. It's e to the negative 6. And then we have a rule of exponents that says if I have my base and I'm multiplying, then I just add the exponents. Okay, so that's why it's 5x technically plus negative 6 or 5x minus 6. And so now this is good because we have our setup correct. E to some power equals e to some power. And so now we drop the base. So we just drop the bases on both sides and focus on the exponent from the left equaling the exponent from the right. And so that equation, we just solved that accordingly. In this case, this is a quadratic equation. And so we just now focus on solving it. Any technique we know. We could factor, use a quadratic formula. This one actually factors. So if we go ahead and set this equal to 0 and factor it, then we solve and get x is negative 6 and positive 1. And we can go again back to the beginning and check both of these numbers so that we can verify that these are in fact our answers. Okay, let's do one last example. This one's an application problem. So between 9 and 10 p.m., cars arrive at a Burger King drive-thru at a rate of 15 cars per hour, or that's 0.25 cars per 1 minute. So the following formula from statistics can be used to determine the probability that a car will arrive within t minutes of 9 o'clock. Okay, so this is a given function. We don't have to come up with a function. This is given to us. And this represents the probability that a car is going to arrive after 9, where t is that number of minutes. So let's answer these parts, A through D. Determine the probability that a car will arrive within 5 minutes after 9. Part B, after 30 minutes. Then graph the function. And then last, what does the function, which represents the probability that the car is going to arrive, what does it approach as t increases without bound in the positive direction? Another way to say this is that as t goes to infinity, what happens to f? Alright, so in this part A, all we need to do is plug in 5 for t into our function, and you can use a calculator for this, and you'll get out 0.713 roughly. And so that means there's 71.36% probability that a car will arrive within 5 minutes after 9. And that's because this function represented probability. So that's why we know that this decimal should be rewritten as a percent, because we tend to write probabilities as percents, and that's what that number represents. Very similar for part B, just plug in a 30 into your function, and so you'll get 0.9994, meaning that 99.9% for probability that a car will arrive within 30 minutes after 9. So, and you can kind of hopefully maybe intuitively understand why this one is so high. 99.9% chance a car is going to arrive within 30 minutes, because we were told that 15 cars will arrive in an hour. So if 30 minutes have passed and no cars have arrived yet, that's pretty unlikely. So it's very likely that at least one will arrive in the first 30 minutes. Okay, so we'll go ahead and use a graphing utility to plot this graph. You can just make a table of values and plug them in to plot it. So you can pick values for t, plug them in and get your f values. Or you can use transformations. Just note there are quite a few. There's a shift here, a reflection with this one, a reflection with this, and compression or stretch on this part. So lots of transformations. So in this one, we'll just go ahead and use a graphing utility. And so this is the graph of that probability function. And just so you know that this hopefully makes sense a little bit to you as well. One being like the vertical or horizontal asymptote here, because if it's probability, 1 represents a 100% probability, and you never have probability higher than 100%. Things are only between 0% likely to happen and 100% likely to happen. So that's why this graph should actually make sense intuitively for us, that it goes from 0 to 1. And so the last part, as time passes, the probability that a car will arrive increases. And so that's, if we just let t get very large, then algebraically we can see what happens, but we can also tell from the graph that we looked at on the previous slide. And so if you want to do it algebraically, if you think about this, e to the negative 0.25t can be rewritten as 1 over that with taking off the negative. If you plug in really, really big numbers here, this denominator is going to get huge. So this is like 1 over very big numbers, and 1 out of a lot is really like nothing. And so it's close to 0. So that term gets really, really close to 0. And then our function was 1 minus that. So this is getting really, really close to 0 when we plug in big numbers. Then all that's left is this 1 in the front. So this function is approaching 1, so f approaches 1 as t approaches infinity. And from the previous slide with the graph, hopefully that also lined up with what we saw. If you remember, it was as t was going toward infinity here, the graph was going up toward 1 right here. Okay, that's it for this one. Just remember, when you're solving exponential functions, you want to make the bases match when you have your equal sign, and then just drop the base and focus on solving for the exponents. Thanks for watching.